So, you know, one of the advantages of online learning is that students that usually are very quiet during class, they do ask questions, you know, during online classes because they use the chat. And you know, the chat, you can send a question directly to the instructor so other students don't see your question. But like I was saying earlier today, I decided to record it because I think it is an interesting class. Magnetism is something that is applied everywhere nowadays. MRI is one of them, and I know some of you will be working on MRI, so I'm going to give a little uh, explanation about how it works. It is a very complex, technology and a complex topic to go over. But I did find a video from I think Michigan State and University is is a very good medical school, um, and and they have some very good explanation there. So I will try to show that as well today. So just to save time, I'd like everyone to enter your name on the chat and just say hi, so I don't spend time. It's going to be hard for me to, go through the roster and ask each one of you to say if you're here or not, or for me to compare. So just send, a chat so I see your name and I will check that on my roster so I keep track of it. Um, so again, thank you for coming today. Let's see how many we have. One, we have 12 students, so there are 8 students still missing. But like I said, I'm recording today's meeting, so if you want to go back and after class, I also want to post the PowerPoint presentation on your Canvas, so you have access to that, and also all the links that I use for the videos are there as well. Okay, so anybody has any question, anything? Okay, very good. Everybody happy that don't have to drive?
Yeah, it's nice.
It's nice, right? You jump out of the bed and you're in the class. So, or you can even stay in bed if you want to.
Yeah.
Yeah, it's really nice. I'm actually at the airport right now, so this is very convenient for me.
Oh, oh, that's great. Thank you. Yeah, I thought it was a good idea to do this. Right now, we are almost at the end of the semester, so it makes sense to maybe use the hybrid option. And next Tuesday, please show up to class. I know it's going to be cold, but we do need to meet on Tuesdays for the hands-on experiments. We're going to have an experiment next Tuesday, so show up. So let me just start it so we don't spend much time. Let's see here. Let me share this and see if I can go. Yeah. Yeah. Uh, so I thought, it was nice to Neil deGrasse Tyson is an American astrophysicist, and he's really famous, and he was talking about, on LED versus old light bulbs. So I thought it would be nice to listen to him just a little bit. So let's start with that. I really like his shows, and let's see here.
Not that anybody asked, but do you ever wonder why the old light bulbs get hot and the new LED light bulbs don't? The old light bulbs, 90% of the energy you were paying for, 90% of the wattage was coming out in a band of light that you cannot see. It was completely useless to you. And what band was that? Infrared. And we detect infrared as warmth, and in the extreme, as something very hot that can burn you. So what LEDs do is take all the energy you need and want in a light bulb and put it all in the visible part of the spectrum. Well, if that's what it's doing, it doesn't need 60 watts, 100 watts to do it. It only needs 3 watts, 5 watts, at most 10 watts, because all that energy is going into visible light. Welcome to the present. Welcome.
Very good. So hopefully, if you see this question, you'll be able to, explain. So I have an interesting question here. Can you guys try to explain? And this is one of those assignments that you write down your initial ideas, then you write your correct, uh, um, ideas and correct answer for this, what's happening there, the right explanation, and then you do a little reflection on your initial thoughts. So this is one of those things that it's amazing. How do you can actually charge your cell phone, your battery, right? Wireless. Where is this coming from? So try to think based on everything that you know so far. And I think we know a lot already. We cover a lot of things about charges, electricity, electronic circuits. We talk about metal semiconductors, insulators, electric fields. So can you imagine how this works? So try to write down. I'll give you a few minutes to do that and document, your initial ideas. That's extremely important, because then you can do a reflection once you get, the right answer there. And for that, I'm gonna pause my video so we don't spend time waiting. Okay, so you had a question, and the question is how the cell phone gets charged on the pad. So if anybody has an answer to it already, you can start. So it looks like Evan, you want to give it right? Yeah.
Yeah, so I think when the charging pad gets plugged in, current begins flowing through the pad, and then when you put your phone on the pad, it kind of becomes like a part of the circuit. So current will move through the pad into the phone and then back through the charging pad. And then the current would move through the battery to charge the battery. The current would have to flow through like the back of the phone. So I'm guessing all the materials would be able to conduct electricity, whether they're conductors or semiconductors. But yeah, that's just my guess.
Yeah, that's a good idea, yeah, but how is the current going, to the cell phone, you just by contact, the cell phone, I don't think cell phone, let me look at mine. I don't think it's metal, you know, it's actually, I think plastic or something. It's an insulator, right? So it's not direct current, right? If we connect a wire on the cell phone, would be direct current, right? So I'm providing energy so the currents go to the circuit, right? But this is, it's just contact, you know. Anybody else? Yeah.
Me, I wanted to pitch in. Isn't it through a magnet? Because a lot, like especially like for me, for example, I have my iPad and I connect my Apple Pen to my iPad like magnetically, and then that's the way that the energy kind of transfers.
Yeah, that's true. You know, it is. You use magnetism there. It's the question is kind of unfair because we didn't cover the topic yet. But I just want you guys to start imagining. Does anybody has this pad already, or Ruby? Do you have the pad, right?
I don't have the pad for my phone, but I do use the wireless charging for like my Apple Pen when I write on my iPad.
Okay. Yeah, it's by using magnetic, fields, So actually, the pad has um, a wire that is wounded on some, piece of iron or metal, and then, it creates a magnetic field. Remember the first experiment, first day of class, first that experiment, that chemist, it's a shame for all physicists, he discovered that the relationship between electricity and magnetism, he was running an experiment to show how batteries work, what a chemical battery. That's what his class, and it so happened that he had a compass, sitting on the table, and when he turned it on, the current, the compass moved, and he said, "What's going on?" Then he turned it off. Then the compass went back to its normal position, right? Um, and the normal position, of course, of a compass, is dictated by Earth magnetic field, but when he turned it on again, the compass changed. So he said, "Oh, there is something going on here," and that's how he found that there was a relationship. So we're going to see today that the same way a wire, or a conductor that has a current going through produces a magnetic field, um, a magnetic field can produces a current on a wire. So if I bring a a magnet close to a wire and I use some motion, I move this magnetic field on a wire, a current is going to show up. So that's the idea here. We have a pad that is producing a magnetic field, and this magnetic field, it's varying. The magnetic field, you have to move, you have to, vary the magnetic field, just AC current. We talked about that last class about AC current, right? The current that varies from positive to negative, right? Positive to negative, positive to negative, right? And that variation inducts a current in another circuit inside the cell phone, right? So now the cell phone has a piece of its circuitry that has an alternating current, a current that is varying. But then remember, the battery is uses DC, uses direct current, right? The battery is positive and negative. It cannot keep changing, because if you keep changing, back and forth, is it going to charge, discharge, charge, discharge? It's not going to work. So, so the idea is that you know, what can you use to convert this alternating current into direct current? What is that device that we can use to do that? What's the name of the device? We covered this last class. What's the name of the device we covered in the last class?
That changes DC to AC?
Yeah,
Is it transistors?
A diode?
well, diode, right? Diode. A transistor, you know, is another step, a little more complicated than a diode. The transistor actually uses to amplify signals, right? The transistor has 3 legs. The diode has only 2, but a diode allows current to go through in one direction, right? When you use the forward biases, remember the depletion region, the interface between PN type and P type, you know, shrinks and allows currents to go through, or it can go reverse bias that the depletion region, you know, increases, right? And then the current doesn't flow on the other direction, right? So that's why, you know, it converts, the current AC into DC. So there is a electronic circuits inside the cell phone that now converts, you know, AC into DC, so it gets to charge, you know, the battery. Okay, so you know that's how it works. So let me let me go back now uh, to that PowerPoint here. So now here you on this slide, you know, you can go, you know, later, you know, at home, you can review this again, but basically this is what's happening here. We have these coils here that, you know, they are producing, you know, this magnetic field. The magnetic field goes and you know, produce a current, right, in the other coil. So there are 2 coils, right? The coil, right? The coil means, you know, wire that is kind of, you know, around and around some piece of metal or, you know, of iron usually. And then the coil, you know, produces this magnetic field. Remember, one wire produces magnetic field. And when you have the effect of this coil, you know, produces a stronger magnetic field, you know, just like a permanent magnet. It has north and south pole, you know. So it is, that's how, you know, it does, you know, it's by what is called induction. It produces a current from distance, right? Not a lot of distance, because, you know, magnetic fields, they get weak very fast with distance, you know, like, you know, gravity gets weak as we get, you know, to the square of the distance, right? But magnetic fields, they get even weaker, you know, with distance. So they're not good, you know, for that. So here you have some further explanation about, you know, the charging pads and, you know, how it works. So it is basically this coil that produces, you know, the magnetic field. Okay. So again, here is the Ørsted experiment. You guys remember first day of class. So we have the wire going through, and then it creates this magnetic field around the wire, you know, perpendicular, you know, around the wire. So so when you put a lot of wires, let's go here. So here, this is the coil. You see here the coil, right? So there are all these images here show everything we're going to cover today. So about magnetism and its applications. So if I have the coil, this is measuring current, you know, ampere meter here. And they have the coil of this conductor, And if I move the magnet inside the coil, this motion is going to produce a variation on the magnetic field, okay? And is this change in the magnetic field that inducts a current, produces a current inside the conductor, right? So when you have a charge moving in a magnetic field, a force is going to be created. Imagine, the same way on the electric field, right? The electric field, if you bring a charge, is going to, create a force. The electric field is actually force per charge of unit, right? It's a charge of one, right? That's the electric field is the force for a charge of 1 coulomb. So here also, magnetic field produces a force on a moving charge. Okay. Now, if I slide this magnet inside the coil and stop, right? So there's no change. There will be no motion. There will be no production of current. So the magnetic the magnet, inside the coil by itself is not going to produce a current. Okay, what produces the current is the motion, of the magnetic field, or the wire, right? So so you can here you on this design here we have north and south. That's the magnetic field. The magnetic field here is not changing, right? Because the magnets are not moving. But if I move the wire, you see this wire moving here, and in a closed loop, you have here a voltmeter. If I move the wire, it's going to produce a current, okay? Because the electrons are going to feel the force of the magnetic field, and they're going to move, okay? That's why. And here again, on the middle, I have also a coil moving and producing the magnetic field, just like a permanent magnet, right? It becomes a magnet, right? I can turn on and I can turn off. If I turn on the current, the magnet is gone, okay? Now, I can increase the magnetic field by introducing a piece of iron, like I have here a nail. You see the nail here, wounded out on the wire and the battery, so I can increase that. So the magnetic field is going to be stronger if I have the nail in the center. As if I remove the nail, the magnetic field is going to be weaker there. Okay, so I have again here different visualizations of how things work. So let me move on a little bit further. The magnetism itself is something that is constantly being researched. So this is an article that I just found it that I thought was very interesting. Actually, this could be an example of a project for some of you if you still undecided what to do. So those are from MIT. Some physicists, they found some exotic particles. So those things that people are discovering every day, new things to explain, magnetism. And this is an example of how things work in very thin layers, not in bulk material, and very thin layers of nickel. You have to remember that when we talk about bulk, samples versus very thin layers of materials deposit, the properties change, and they are able to observe how things behave. And this here is, what they call exciton, hopping from one place to the other. The exciton is based on the article is a combination of electron and hole. So the electron and hole, they are somewhat connected. Remember when we're explaining how superconductors work, we're talking about, couple, of, two electrons that kind of move together, right? And that kind of explains how superconductivity works. So here again, it's another example of how the whole electron combine, even though they kind of, seem different entities, but they are connected, and the effect of them being there, cause some properties, different properties. So it is the interaction between these two particles, electron hole, that is what is called excitron. So I just thought it would be interesting to show. This is some pictures that I taken from another book that I use also for a different class. But here, where the word magnet comes from, actually there was this guy, called Magnus, and he kind of was the one that the first recorded, probably other people have seen that happening, but it's one of those things in science that is interesting. Some people, sometimes they just go through life and things happen around them and they don't pay attention, like, the apple fell many times, I'm sure, but Newton, I don't know if that's true or not, but, but Newton is the one that, looked into it, and thought, well, why is this thing falling? Maybe fell on his head and, he got upset and tried to answer to that. But, so this guy apparently, was walking close to some rocks and he noticed that some of his nails on his boots were kind of attracted to this rock. And he thought, wow, this is something here. There is something here. So, and so that's it's curiosity reading for you. And when we don't know things, we all find it mysterious, and, so we try to claim, whatever, try to explain. Now, this is kind of interesting, kissing stones, and I found this, the Chinese called loving stone, obviously, because they attract each other here. So this thing called kissing stones. I thought it was kind of interesting. And I'm not Chinese. I don't know if anybody can read Chinese, but he's saying they call Tzu Shi. I think that's how we pronounce here. But I don't know if you know any Chinese, try to say that and see what happens. Magnetism from moving charge. This is one thing that, remember I was saying the magnet needs to move or the wire needs to move on a magnetic field. It's this change, it's this that causes, induction, that produces current, the same way we were talking about the pad, right? That has the current that was varying, so it inducts current on the other wire, right? So this is basically the principle of generating electricity, right? Generators work based on magnets. They are not moving, but hydroelectric has potential energy with all that water, right? And then when water, falls, it produces some mechanical energy on a turbine. The turbine start moving, and it's this motion through a magnetic field that produces electricity, And this is true for, wind power, that, you have these big blades and and then the wind moved the blades, so the blades are moving. What you have there is an electric generator. Basically, it's just, a set of magnets with a coil that is moving, right? The coil is moving, and you have these magnets. There are, stationary, maybe sometimes 3 or 4 of them. So as the coil moves around, is producing, electricity, right? Electrons that are inside the conductor feel the force of the magnetic field, so they feel compelled to move in one direction. And that's the beauty of this, so it has to have moving charge, okay? It has to have the magnetic field needs to be moving, or the wire needs to be moving. So the magnet can be changing, like, on the pad, you have the current going through a coil. The coil produces the magnetic field, and the magnetic field is changing constantly, and is affecting the other coil that is, above inside the cell phone. So this is a little more for you to read here, explaining about the electron itself, has a spin. They call it spin, but it is. I think I talked about that before. That the electron has a spin, but and acts as a little magnet. It's not really turning, going around its axis, because when we talk about spin, it looks like it seems to you, it might seem to you that, oh, the electron is moving around and around. No, it's not about that, but the electron and the proton, also have this spin that is a little magnet, right? A little magnet. So it has a north and pole, right? It's one of these magic things, abstract things that, we create this model to explain how things work. And so it has an angular momentum that is not due to rotation, like in a classic, if we have a basketball is rotating, it has an angular momentum there. And we know this is what we understand about angular momentum in microscopic world, but in the microscopic, macroscopic versus microscopic, that's the difference, like basketball is, microscopic world, we see things rotating, and that causes an angular momentum. But on my microscopic world, the protons and electrons, we assign spin, but it has an angular momentum, but it's not due to is due to their nature, of being that small, things are small, and they have their own, nature of behavior, right? So, uh, so that's going to be an important thing to keep in mind when we start explaining how MRI works. So now there is also, you see, when I create a coil, I create, a magnet, right? That is like a temporary magnet that it exists as long as I have a current going through it. Now, we have permanent magnets, okay, that, are just in nature, things that are already, built that way, right? And that you can imagine if the protons, usually in metals or materials, the spins of protons, or atoms, they are randomly distributed. So that means their directions go to everywhere, right? So, and then the magnetic field cancel each other, right? If I have two magnets, they're going to cancel each other because one goes this way, the other goes the other way. So, and there's no result of the sum of them, right? But some materials, by nature, everybody's different, nobody's the same. So some materials by nature, they all aligned, in one direction, or most of them are all aligned in that direction. And that, well, is what we call permanent magnets. So they are their way. Now there are some materials, ferromagnetic materials, that a piece of iron, for instance, that we can induce them to become magnets, like temporary magnets, if we introduce a piece, a nail, for instance, that is a piece of iron, in a very strong magnetic field, that is going to force all the spins of, all the atoms to have the spins in one direction. Okay, and with that, then when you remove them, they still have the magnetic properties, because they still have all their spins, in that directed in one direction. So they can act as magnets, like temporary magnets, Um, so, so let's see what's next here. Oh yeah, short range magnets. Like I was saying, magnets, the magnetic field, doesn't have a long range. They have to work really close, together, like the pad. If you ever buy this, you can maybe do some experiments. You can put the pad, right, touching, the cell phone, or maybe you make a little, a short distance, maybe 2 millimeters above. Maybe you try next time 5 millimeters, then you try, 1 centimeter, above the pad, and see if you get the charge at all, And I'm probably what I predict, is that probably the charge is going to take longer and longer, because the magnetic field is weaker and weaker, and at some point, it's not going to work at all, Okay. So electromagnetics. So electromagnets means that it's a magnet that works through electricity, right? So so you have current going through a coil, so to produce magnetism, similar to and then you have superconducting electromagnets. Now is a electromagnet that has a superconductor as the as instead of copper, for instance, there is a regular conductor, right? You use a superconductor. And why is that? Well, applications like MRI requires a very strong magnets. They all electromagnet. They're not permanent magnets that they use there. They use electromagnets. But now you have to think, why do you need a superconductor, on a very strong, can anybody come up with a reasoning why we need to do that? It's just to check if you guys are not sleeping, or are you still awake, or yeah. So the question is, what is an electromagnet? You have permanent magnets that are materials, that they have produce magnetism. They have magnets. A magnetic field produces a magnetic field by just nature. All their spins, all the little magnets, inside the atoms, they're all lined up in one direction. So they have north and south due to the their characteristics, the material. but we have electromagnets that, devices that produce the same magnetic field, but now is with electric current going through the coil, right? A current going through a wire itself produces, a magnetic field. So if you have a coil, you have a stronger magnetic field. And so now the question is, why do we need superconductor, to be used in on an electromagnetic device?
Well, wouldn't it like be able to move the electricity on the devices?
Yeah, superconductor offers there is no resistance, right? So the current can go very high, and then it maintains itself, right? It keeps running continuously because uh, there is no resistance. So you start the current and the current keeps going. You don't need to apply more current to it, right? And the fact that it doesn't have resistance, what is the implication? If a circuit that has no resistance, what happens to it?
It wouldn't heat up that much.
Exactly. When you have regular conductors and you're going through a lot of current to produce a very strong magnetic field, because that's what you need for MRI, you're going to have a lot of heating, right? It can get very hot and can even melt. It's dangerous, right? So what they do is they cool down the wire so they can have a superconductor going through and they can reach very high currents and very high magnetic field. Okay. Well, that question was just to make sure you guys are with me. So is this going okay? Everybody, are following me on this, or do I need to stop or have any questions?
You
Okay.
can
No,
keep
we're
going.
following along.
Yeah.
We're good.
Okay. All right. Thank you. Thank you for the feedback. So, yeah, so here, magnetic materials, special role of iron. So this again, I think I already said that when I have a battery going through a coil, it produces a magnetic field. And when you introduce a piece of iron like the nail, the magnetic field increases. Okay, so that's one thing that. Now, one thing that is very important to understand is that heat itself destroys magnetism. So if I have, what we call when it reaches this, what's called Curie temperature, uh, the magnet field gets, destroyed. It doesn't work anymore. So Curie is this person that discovered that after a certain temperature, magnets don't work anymore. And can anybody imagine some sort of mechanism why this is happening?
For me, when I think of it, I think of like something frying like a cable or something, like it was just so hot or something that it just kind of like blew out.
Yeah, well, if you increase the temperature to a point that things melt, right? Then everything is destroyed. But the Curie temperature is not really a melting point temperature. There's a certain temperature. The piece is still solid. It didn't melt, but after a certain temperature, what I want you is to have an eye inside the material. What's going on there with the atoms. Well, as you increase the temperature, what has created the magnetic field on these permanent magnets, and what happens when you start increasing the temperature that basically, deteriorates its properties, its magnetic properties deteriorates, Anybody want to give a stab on it on this one?
I can try.
Yeah,
So if like the temperature is low, the permanent magnets will like all the electrons will have the same spin and will be pretty even, but as temperature increases, maybe the spin won't be like the same direction or the same speed. Things will start getting uneven and it'll weaken the magnetic field.
exactly. As you increase the temperature on a permanent magnet, it turns to be like a regular material. A regular material has also atoms. All atoms have spins, but the fact that they are randomly distributed, they don't have magnetic properties. In combination, right? A collective action, magnetism is a collective action of all atoms having the spin all lined up, they all very disciplined, they all uniform, in one direction. They all have the same goal, right? But in a regular material, they are randomly distributed. So, it doesn't have, overall effect of showing a magnetic field, a northern pole in one direction. So as you increase the temperature, this organization deteriorates because of vibration and because of, the spins start to turn around and going in other directions. Very good. So you can read this further. We already now. North Pole and South Pole. Now let's talk a little bit about Earth. We have Earth as the North Pole and the South Pole. Anybody has any idea why we call North Pole the North Pole and South Pole the South Pole, or what's happening there? Now, let me give you a little bit of information. When you have a compass, right? The compass points out to the North Pole, right? The compass is basically a needle. There is a magnet, right? And the magnet of this needle, the north of that needle is pointing to the North Pole. So can you explain why this is happening? Why? So do you understand my question? Yeah, it's true. The Earth is a big magnet, right? And we have this magnetic field. And thanks God we have this magnetic field, because it really, makes life possible on Earth. If we're not for the magnetic field on Earth, we would be just like Mars. Okay, what about Mars? Mars has no magnetic field. I don't know why Elon wants to go, live there or something, because the place is not safe. First of all, maybe a long time ago, it was just like Earth, maybe, we don't know that. We didn't find anything yet there, that shows that there was life there or anything like it. I didn't see any trees, any fossil or anything like that, But the truth is, its atmosphere is 1/3 of our atmosphere. And if Mars had an atmosphere a long time ago, maybe there was life there. But today, the atmosphere is very thin. And why is thin? One answer could be due to the fact that they don't have a magnetic field. The magnetic field protects its atmosphere from the solar wind. Solar storms, are basically very energetic particles that come and they bombard everything out of it. They're blowing away the atmosphere in Mars. So that's why it's getting thinner and thinner. and at some point there will be nothing left. So unless Elon, he is very smart, maybe he can create, a magnetic field inside Mars, and that will solve the problem. But then they still need to thicken up that atmosphere to make it, livable like Earth. So the fact that we have a magnetic field is, is the reason we are here today. All right. Now, my question is, why the needle of the compass, the north side of that little magnet, right? The needle is a magnet. Why the north is pointing to the North Pole?
I can try.
Go ahead.
So I'm guessing that I remembered there was like a video on the Orsted experiment where when he held the compass next to the circuit, the needle pointed in the direction. I don't know if it was of the magnetic field or it had something to do with the needle changed directions in proportion to the circuit. So I'm guessing that the needle points north because of how the magnetic field works with the North Pole and the South Pole.
Yeah, you are quite there, but there is one word that I want to hear, what is happening on the North Pole, what kind of what is the pole on the North Pole? I think that's the question that I should ask, Um, when you have two magnets and you try to bring them together, and one is north and the other one is south, what happens to the magnet? Are they going to attract or are they going to repel?
They attract.
They're going to attract. If you have um, two poles that are the same, north and north, what's going to happen? They're going to
Repel.
repel. So what kind of pole do we have on the North Pole?
Positive?
Not positive.
Negative?
And we say north and south, pole. So if the North Pole of the needle, right? The needle is a magnet. So if the North Pole of the needle is pointing to the North Pole of the Earth, right? So what is that a North Pole, magnetic North Pole, or is a South Pole? When we talk about North Pole, it's a geometric pole, on Earth. We call that North Pole. Actually, the Earth North Pole is actually a South Pole there. Okay, the magnet is the south. We call north maybe because the needle, the North Pole of the needle is pointing to the north. So it's kind of semantic, but what actually is happening is that on Earth we have actually a magnet that is it points to the South Pole. The North Pole is a South Pole. You see, that's the title of this thing that I'm trying to explain, so you guys can read more about that. Another thing is that it doesn't coincide with the geometric pole. It's on an angle, and other planets have the same kind of characteristics. So now, what is the source of the Earth and magnetic field, and how is this generated? Anybody has any idea how this magnetic field is generated? It's inside. It comes from inside the Earth. We know inside the Earth is is very hot, extremely hot, right? So if the Earth, the core of the Earth were a big magnet, right, a big permanent magnet, okay, then we know current temperature deteriorates permanent magnets. So how is it possible that a core that is extremely high in temperature, everything is molten already, how come that creates a magnetic field? Can anybody visualize that? Try to write it down if you have any ideas, and then compare with the answer that I will provide, or at least nobody really knows these things. It's just theories. So I would tell you what is the theory right now, and of course, this is a very complex system. So if you can imagine how is the magnet uh, generated inside the Earth. If you come up with an answer, you can raise your hand and talk about it. Try to be creative. This is your opportunity to imagine things, and write down, what you believe, might be the reason. It doesn't really need to be the correct answer. It's actually exciting if it's not correct, because then you use your imagination, and that's what this kind of questions that I pose to you is intended to, is for you to explore your creativity. That's a difficult skill to develop. Learning is not just acquiring information. We can acquire, and nowadays with AI, what is the purpose of acquiring information? Maybe the only way we can beat AI is to develop a creative mind, ability to imagine things beyond what you know, and try to, put down in words what you are imagining. So this is, the kind of thing that, we should try to explore and to develop, okay? Because just acquisition of information, books have a lot of information, and now, you can put all this in a computer, and they can reproduce all knowledge. But how to gain new knowledge, that, goes really with the imagination. All the models that we're discussing here was imagined by somebody, and then they tested, and that's what science is about. It's about this ability to imagine new things. So can anybody try to
I think I can give it a try.
okay.
So the question is asking how is a magnet generated inside the Earth? So if we're taking a look at our inner core, because you say it's really hot, so it's like a molten big piece of metal like iron, and its outer core is in a liquid form. So as the outer core flows around our inner core, it kind of creates like an electric current, to which it causes like a magnetism.
Yeah. So basically, we have a lot of different. This is a very complex system. You have to understand the fact that you know, you have nickel, iron, you know, other materials going through, and some have more electrons, some have less electrons. The temperatures are not, you know, uniform distributed either. So some have high temperatures, some have lower temperatures. So with high temperatures, some materials produce more current. We know semiconductors produce more currents when it goes at a different temperature. Electrons are moving, you know, faster. They have more energy. So that creates differentiation of concentration of electrons in different locations. And if you have different concentrations of elements in one, the tendency is for them to move to other locations, right? If you're in a room that is very crowded, your tendency is to, you know, move out, you know, so you know, too many people here, so you start moving, you know, and dispersing. So that together with the motion and start creating some current, and all you need is a little current to create a magnetic field, right? And the magnetic field creates more current. So it's kind of a snow effect, you know, a snowball effect, right? You know, and that's how I imagine, you know, nobody really knows about it. Everybody has some theories here and there, but basically this is what people think is happening, you know. So this is an exciting field because, you know, people, you know, still studying this. So basically, this is what the question that I had. You know, how come, the fact that at high temperature and they still a magnet. So, you know, some explanation here. Einstein's mystery. He thought this was, you know, one this thought the origin of Earth's magnetism to be one of the greatest unsolved problems of physics. So another aspect of magnetism on Earth is that every so often, you know, and I say every so often, for us it's millions of years, even though geologic record that seems very fast for them, you know. But something happens, you know, that the magnet, the pole, North Pole turns to be South Pole, and South Pole turns to be North. You know, there is this flip of magnet. Nobody really knows what happened. Maybe, you know, there is some motion that start moving in a different direction or something of that. So inside the Earth, we have a different because of the heat, you know. So then you have a convection because, you know, different temperatures, liquid iron and nickel, they move, you know, up and down. Then you have the Coriolis effect due to the Earth rotation. And then you have the dynamo effect. The dynamo effect is basically, you know, generation of current due to magnetic field, and then this self-sustaining loop that once, you know, we have magnet field creates current, current creates magnet, so there is slope. I found now this picture here is a visualization of the speed of the currents on the core. So you see things are not uniform either, you know, and of course it's expected because, you know, the Earth, you know, is a mix of a lot of different things, different materials. So it's not going to be, you know, perfect, all symmetrical kind of, circuitry. So things move, you know, depending on you have maybe more liquid, more higher temperature here or there. So, so this is interesting to see. So does the Earth geometric pole coincide with the North Pole of Earth magnetic field? So the answer here is no. So you guys can, what happened here? I have this diagram here. You can remove that. For some reason, I can't remove it. Let's see. There's some. Okay. Let's go back. Oh yeah. Okay. Now I can move this. Now I created some different things here. So the answer is here. So you guys can review this at home. But basically, I have this picture here that it's very telling. That the axis of rotation does not coincide with So you look here on the north, and you see south magnetic pole. So the magnetic it is the north pole. We call geometric north pole is but from the magnetic field, it is actually the south pole, and that's why the needle, the north pole of the needle points to in the direction of the north. Okay. Now I want to show this. This is a video here. I have the link here. I want to show this video. This is a very interesting video here. So let's look at it.
Thermometry.
What, if it gets too hot, you're in trouble, or?
Sodium expands when it heats. The vessel has a certain volume. There's a temperature above which it's overfull.
So here, what they're doing basically is they're trying to reproduce, the Earth in the lab, the molten part of it, and try to figure, how the magnetic field is coming. Where is this coming from? So this is a very, I would say, it's interesting, but also probably expensive experiment, and very difficult. So so this is just to illustrate, how far we can go in science to get answers, and things are getting more difficult because we're trying to explain things that are really very complex. So let's see how they do this.
Full, and it's better not to be overfull.
What temperature is that?
I think it's around 130 degrees.
Have you ever been close?
No, because our thermometries we have thermometry and backup thermometry and backup to the backup thermometry.
Let's back up and explain, what is this thing?
This is a 3-meter sphere of molten sodium.
That is 12.5 tons of hot liquid metal, designed to spin at up to 4 revolutions per second.
3.95 Hertz.
And at that rate, the outer surface of the sphere is moving at over 130 kilometers an hour. That's over 80 miles per hour.
And basically, it's representing the Earth. What they're trying to do is find out how the Earth's magnetic field is generated.
And some of the first scientists to study this, starting with William Gilbert in 1600, proposed that the Earth was a huge permanent magnet. Now today we know that the inner core of the Earth is solid, and it's mostly made up of iron and nickel, which are ferromagnetic elements. However, the temperature of the inner core is nearly 6,000 Kelvin, which is way above their Curie temperatures, and so there is no way that they could maintain a permanent magnetic field. The same is true of the solid mantle of the Earth. Much of it is way too hot for permanent magnets, which leaves only the liquid metal outer core as the place where Earth's magnetic fields could be generated. And this is what is modeled by the 3-meter spinning sphere of molten sodium.
It needs to be as large as practicable. It needs to be as high speed as practicable. And we use liquid sodium because it's the best electric conductor of any liquid. So that has the downsides of being hazardous and flammable, but the failure would be modestly catastrophic. That's kind of a weird twist of phrase, but
Modestly catastrophic.
yeah.
Most buildings have sprinkler systems in case of fire, but not this lab. To see why, take a look at a single drop of water falling on a single drop of molten sodium.
Every staff member syncs with Dropbox. All the files that you may use are
Now multiply that by 12.5 tons, and you have modestly catastrophic. But the researchers have thought about this and they have a plan.
There's a liquid nitrogen dewar that sits up top. So one of these, mostly full, you can just hit a switch and dump the entire contents of liquid nitrogen on top of the experiment.
So this is like a physicist's super fire extinguisher then?
You know, it's a backup plan. The plan is no leak, no fire. The backup plan, put the fire out with cryogenics. It actually works great. This is 300 degrees colder than the sodium. And so sodium cannot burn in nitrogen gas atmosphere, and the cold freezes it, and the leak gets frozen, and everything just chills.
But when everything's working normally, how is a spinning sphere of liquid metal meant to generate a magnetic field? Well, for the Earth, the thinking goes like this. First, as the Earth radiates heat into space, its core cools. This means the solid inner core is growing, as iron and nickel from the outer core solidify at the boundary. Now this leaves some lighter elements, like sulfur for example, behind in the outer core. And so patches with those lighter elements experience a buoyant force and rise away from the core in turbulent convection currents. Now add to this the fact that the Earth is rotating. The rotation causes those convection currents to spiral around an axis roughly parallel with the Earth's axis of rotation. These spiraling turbulent flows of liquid metal can trap magnetic field lines, and as they move and stretch the field, they create electric currents that produce more magnetic fields. If the magnetic fields are generated faster than they dissipate due to the resistance of the metal, well, then you have a self-sustaining electric generator, or a dynamo.
We talk about the dynamo generation of magnetic fields to mean when you have a turbulent conductor, let's say convecting like the core, that spontaneously generates a magnetic field. If you have a little bit of current that happens, it causes a little bit of magnetic field that couples into the motion, that causes more currents, causes more magnetic fields, that couples into the motion, and then you're just converting motion to currents. But it goes unstable.
That's kind of counterintuitive though, because you started out with no magnetic field, so how do you get the current in the first place? You know what I mean? Like
Just all you need is a little infinitesimal amount, a thermal variation, a random current will just grow to full size. So once something's unstable, actually you don't really care where the tickle came from. The states we have now don't generate their own magnetic field, so we've not reached the dynamo threshold, although the hope is to do so in a modified version of the experiment. So we apply magnetic fields from the outside and then look at the amplification of those magnetic fields by the rotating turbulence. And we get copious amounts of amplification depending on where we are in the operating conditions. For instance, when we apply these external magnetic fields, sort of go through the experiment like that, they get twisted up by the flow, and the magnetic fields in the angular direction can be up to 10 times larger than the fields we apply. So we actually have lots of gain, even though we not yet have a closed-loop dynamo.
So why is it important to understand the Earth's magnetic field?
We know the Earth's magnetic field is part of what makes the Earth a habitable planet. One of the ways is that it forms a shield, the magnetosphere, which deflects the worst parts of the solar storms around.
But lately that shield appears to be weakening.
So the Earth's magnetic field has dropped 10% in the last 170 years. We don't know why. There's a very weak spot of the Earth's magnetic field in the South Atlantic anomaly, that's growing weaker. We do know the Earth's magnetic field has reversed many hundreds of times in its history. We don't know where it's going now. We actually don't currently have a predictive science of the Earth's magnetic field.
Why is that important?
So the Earth's magnetic field has weather, it has changes. You might want to have a forecast for planning purposes.
Will this spinning sphere make that forecasting possible?
It's an experiment, so no one has run a device like this ever. It's world unique, so you don't entirely know what's going to happen when you run it. But that's why we do experiments. So in fact, we don't know whether it's possible or not to predict the Earth's future magnetic field. It's an open question.
Hey, so in about a week, I am taking the 13-hour flight to Sydney. I am touring the country and launching a new feature-length documentary. There's more info in the description. But on that flight will be my wife and my 2 kids who are 2 and under, and I kind of have these visions whereby if I do get a moment to myself, I'm going to sit back and relax with the sponsor of today's video, which is Audible, the leading provider of audio. I would love to learn more about the country and about his experience of growing up there, not to mention the fact that it is a very, very fun.
Okay, so that's, showing how science works, and basically somebody, wondering how magnetic field is created, then they design an experiment, and they try to, reproduce Earth, and probably very expensive experiment. So now let's try to see, how MRI works. I have a couple of videos here, on the links. So basically, how this is basically what an MRI is a big magnet. So we have a patient there, and that's what is the input of that. So we apply some basically some signal, and see what the response on this since the body has a lot of hydrogen has spins, and we can align these spins. If you apply a magnetic field to it, then we can stop to apply the magnetic field, and you can see how long it takes these spins to become random again. It's like a, remember when I was talking about, creating temporary magnets, right? Basically, we put a material inside a very strong magnetic field, and we force all the spins, all protons or atoms, to line up in one direction. And when we remove them, it takes some time to become random again. Of course, this randomization timing, they call this relaxation time, is going to depend on the material, right? If we have a body, body has different tissues, we have fat, we have water, we have bones, we have, and the relaxation time, this time that it takes to, go back to its random, is going to depend on the tissue. So here the output is an image like that is basically, due to this effect of relaxation time. So here is an example. They have identified here some growth or something different than the regular tissue. So that's, what MRI can do, can go inside and see things. And mostly here again is this decay here is the decay is the the signal of having these spins being going back to its random position, so it takes time for that for different tissues. So here is, I think it has more fat, and fat will respond differently than from this tissue here in this location. So so it is basically this amount of decay on the time of the spins that what is translated into contrast, and that's how it works. This is in general. This is a very complex, but this is. I just want to give you an insight right now. So we'll go in more details later, showing here how what you can do to identify different aspects. This is an example aneurysm. You see here. You can expand this if you want. To see things closely. And once you have these slides yourself. So so basically, what we have here is what we call longitudinal and transverse plane. What longitudinal means, it means in the direction where the body is laying down. That's the z-axis here, and transverse plane is the x and y plane here. Okay, So nuclear magnetic resonance. And by the way, MRI, was first called nuclear magnetic resonance, because basically this is what is the physics behind this machine. And they changed it to MRI later, because nuclear, it's kind of a scary thing, people to, to hear. So it's basically, plays with this magnetic moment, right? The spin, right? I was talking before, and this spin has a vector, and when you turn on this big magnet, it creates a magnetic field in the direction of uh, the body here. The body is lying, right? So with that, all your spins are going to be lined up in the z-axis. You see here on the bottom a picture of atoms with spins going all over the place, all randomly distributed. So your body at this moment, when the magnet is off, you have a lot of liquids, hydrogen in your body. Proteins have hydrogen, everything has hydrogen, and the spins are have a random direction. It's not aligned yet. But when you turn on the magnetic field, you see here this line here, this blue line. So this then the atoms have a tendency to line up with the magnetic field. It turns out that not all of them will have the same direction of the magnetic field. So we're going to have what is called a parallel state of spins and anti-parallel. So it's right here, if you see that, parallel and anti-parallels. So parallel and anti-parallel states, okay? So, but you can see here at this point that, most of the spins are on the same direction. That's the parallel state, and few are on the others. So this is a fact. Now, in addition to it, it's not that they are fixed all in one direction, but there is what's called a precession. So precession means, the vectors are themselves kind of going around, rotating, not completely lined up and fixed. Now, how are we going to get images out of here? So what they do is they apply another magnetic field here, now in the perpendicular direction. And what happens is with that, at some point, is a radio frequency, a magnetic field. It varies, right? And what it does is at some point, is going to induce all these spins to line up perpendicular. And if they do that with this variation of going up and down, is going to cause a signal on the coil of the magnetic field. So we're going to detect that variation, is going to produce a signal, and that signal, the measure of that signal is going to be utilized to create images. So what happens is, you see, when I apply this radio frequency magnetic field, in the perpendicular direction, they're going to be now perpendicular to the z-axis. And once I turn off, then this lined up is going to, go back to its position, lining up to Z. And this decay, and this is what is measured here on this graph. You see that graph decaying here. This decay is what they call the T2 star. This is one of the parameters that are measured, to define images. Here, the vertical precession, is showing, the spins all around. And it's like one slice, perpendicular to the Z-axis. You can see, all the spins moving there. So it is this process of loss of magnetization that is it happens independent from the longitudinal magnetization. So there are two parameters that are measured here. The one thing that is to keep in mind is that these two measurements, the T1 and T2, they're basically the time of decay of this relaxation time. One related to the Z, the net magnetic magnetization, and the other one perpendicular to it, the longitudinal and the transverse magnetic field. So this decay is two measurements of the decay that are used in the imaging. So let me show you now, another video that goes through this in a little more detail, and they show some better images. So it's going to help you to understand what's going on here. Okay. This is actually a video from the Michigan State.
Dr. TMD here. I'm so excited to bring this all to you. We're going to laugh.
See this? This is a 400-ounce bar of solid gold. Back in the 20s, this could buy you a...
We're going to laugh. We're going to cry. We'll probably cry more than we'll laugh, but at the end, I promise you, you're finally going to understand what all those spinning arrows mean. But first, a word of warning. MRI physics is hard. Like, really hard. As the great philosopher Prometheus Lionheart once said, nobody understands MRI physics. And usually those pretending to know show something like this. Here's a diagram with arrows. Some are aligned one way, some are aligned the other way. Here's a diagram with a bunch of squiggly lines. We'll talk about the terms frequency encoding and phase encoding. We'll maybe show a picture like this, and we'll say that from all of that we generate this. Any questions? But there actually is a logical story behind all of this, and I've spent hundreds of hours searching out every single resource available to bring the full story to you. I want to start this lecture series by looking at something that at first seems totally unrelated, but it will highlight an important point. This is a picture of an F-22 Raptor, the most advanced airplane ever built. In fact, it's so advanced, it can't even fly. Now I know what you're thinking, it has to fly, or that would just be ridiculous, and yes, it actually does fly. But if you shut off all the electronics on this plane, it would tumble out of the sky. Every subsystem of this plane is likely a postdoctoral level subject. The person who designs the wings doesn't know what's going on with the engines. The person in charge of the control surfaces doesn't understand the electronic systems. And when you see an image from a modern MRI machine such as this, it's the same situation. These machines are so advanced that there's an expert designing every single component. The main magnet, the transmit coil, the receiver coil. So how in the world do you begin to learn something so advanced? When it comes to airplanes, you would start by examining something like this. This is a picture of the Wright Flyer, the very first time humans took to the skies and sustained flight in 1903. Now this is something you can actually calculate by hand. So if you want to begin learning MRI physics, where do you start? How about here? This is the first clinical MRI of a live human being taken in 1977. And this is something more manageable to begin learning. And most MRI physics resources out there are teaching you things related to this level of physics, not the fancy images we see today. But remember, this plane has to follow the same physics that this plane follows. And this MRI machine has to follow the same physics that this one does. So if we build a solid foundation, it will go on to serve all of your future educational ventures into MRI physics, and that's exactly what we're going to do at these lectures. So warning, you're about to be hit with a ton of bricks. The good news is you may have heard and know a lot of the terms we're going to talk about. The bad news is they haven't been taught in an intuitive way. And the ugly is everything else about MRI physics. So this is the outline we're going to follow. We're first going to talk about nuclear magnetic resonance and this amazing phenomenon we take advantage of in order to build these images. We'll then move on to discuss signal localization, which is essential for us to be able to build the picture. And finally, we'll discuss image contrast, where it comes from, and how it makes the pictures look like they do. And the good news is, this is 99% of what you need to know to be able to be a good, God-fearing, and/or respectable radiologist/scientist. But wait, there's more. We have this unique concept to MRI physics, the dreaded K-space. It's such a confusing topic because it just comes out of nowhere. People just start talking about K-space, and they don't explain why it even exists. Why do we have K-space? The story is actually fascinating, and in order to explain it, we need to understand four things. The MRI equation, and then how this relates to building an image. And these constitute the full, complete story of MRI physics. And if you're interested in this, let's get nerdy together. So the goal, we want to take advantage of a complex physical property and build an image. In order to do this, we have this machine that we call an MRI machine. It's going to receive some inputs, and it's going to produce an output. And from that, we're going to be able to build this image. So first, let's start by talking about the phenomenon that makes this all possible. Nuclear magnetic resonance.
Hey, this is Eugene Vidman, and I'm his older brother, Alex Vidman. Today I'm asking.
So the story of nuclear magnetic resonance begins with the proton for MRI imaging. This is a diagram of a hydrogen proton. Notice that the proton is charged, right? It has a positively charged nucleus, and it also has a spin, and it has a radius. Now, one of the interesting things is, since it has a charge, a spin, and a radius, that you can model this as a current flowing through a loop at radius r from the axis. Think about it. What's an electromagnet? It's a charge spinning through a loop. And since this behaves like a little magnet, it's going to follow magnetic field lines. Just like a compass trying to align itself with the Earth's magnetic field lines as shown in this picture, our proton will want to do the same. It behaves like a magnet, so any magnetic field we put it in, it will try to align itself with that field. So how does this come into play when we stick a human inside a magnetic field? In this diagram, you can see that we have our stick figure here laying inside these magnets, and the magnetic field they're generating is going in this direction. If we could take a cube of matter and zoom in on it and look at what the protons are doing, we might see something like this. Notice that within this cube, we have two options. We have protons lying with the magnetic field, and we have protons lying against the magnetic field. And notice that there's slightly more protons aligning with the magnetic field than against. Now, why does this happen? It turns out the direction lying with the magnetic field is slightly more energetically favorable than that lying against the magnetic field. If you were to add all of these up, you would have a sum total going in this direction with the magnetic field. And that actually creates a magnetic vector in that direction. We are literally creating a magnet inside the body by having these align slightly more with the field than against. Now, this effect is small. We're talking a few protons out of a million. But if you think of how many protons there are in the body, billions, maybe trillions, then the effect magnifies, pun intended. And the stronger the magnetic field, the greater this effect. So throughout this lecture, we're going to ponder some conceptual questions. A lot of these are questions I had when I was trying to figure this out. So does the net magnetization immediately develop as soon as the object is put into the magnetic field?
So this is a key question. And I think, what would you say, to this one? Can you just think a little bit, basically, what he's saying is that, remember I said you have the parallel and the anti-parallel, lined up, right, of the spins inside your body. Well, the sum of all that creates what they call the net magnetic, field, right? Because you have more onto one side than the other one. So when you subtract, so you're going to have, a net magnetic field created in your body in one direction. Now, he's saying that, so as soon as you put your body in this magnetic field, turn on the magnetic field, this develop, immediately, or it takes some time.
Would it be immediately?
Or maybe a better question, does anything just instantly happen in life? So the answer is no. It takes time for it to reach its maximum value, growing as a simple exponential with time constant called T1. More on this to come. You may have.
So this is the time that is measured. This time of, how fast you lined up, of course, is going to depend on the tissue, right? So you can imagine, healthy tissue and diseased tissue is going to respond differently on this alignment. And the measurement of this delayed of alignment is what creates the contrast. Okay, so less time, more light, or more time, less light, and that's how they create images. Is based on this alignment. Okay.
Have even been shown a graph that looks something like this. Here we have net magnetization along the y-axis, time along the t-axis, and we can tell that something is growing with respect to time, reaching a plateau at some maximum value. So
it's important to understand this, and important to understand that different tissues are going to respond differently. Okay, and that's the basis of generating the image and the contrast. Okay.
Let's illustrate this a little bit better. Here's our stock model. I think his name is Noah. If not, we'll still call him Noah. The guy needs a name. So Noah here is waving to us. And what we're going to do is, again, look at a little cube of matter inside of Noah. In its natural state, we're going to have protons arranged randomly within this cube of matter. Now we're going to take some electromagnets. We're going to run some current through these coils. And we're going to produce this magnetic field that we're just going to call B0. We move Noah into the magnetic field. And let's see what happens to the protons inside his body. They're going to align, as we discussed before, right? Some protons are going to align with the magnetic field, some against. There's going to be more aligning with than against, and this is going to produce a net magnetization along the same direction of our applied magnetic field. We call this magnetization M-net. But on its own, nothing happens. We haven't imparted any extra energy into the system to make this move in any particular direction. So let's see what happens if we're able to somehow push this magnet into a different orientation. Notice how all the protons inside of this initially keep their respective alignment, all turning together as the net magnetic vector is reoriented. So what happens when we let go? The net magnetic vector we created in Noah's body begins to spin, or precess as we call it, with respect to the applied external field B0. Now the amazing thing is, this precession is predictable and occurs at what we call the Larmor frequency, which is a very simple formula that's going to govern everything that we do in MRI physics. The formula consists of a gyromagnetic ratio, which for hydrogen protons is constant at 42 megahertz per Tesla, and then the strength of the applied external magnetic field. For a quick example, if we have a 1.5T magnet, the Larmor frequency will be calculated as 1.5 Tesla times 42 megahertz per Tesla equals 63 megahertz. For comparison, a local AM news radio station may broadcast at somewhere around 68 megahertz. This has important implications which we'll talk about shortly.
We're a team of funeral professionals, scientists, and software engineers. We have a complete...
So here's an important question. How do we push the net magnetization away from our main magnetic field B0? Do we simply stick our hand in and start poking the body? I wouldn't recommend that at your practice. So let's think about this a little bit further. We kind of gave the answer away in the slide before. We introduce a new oscillating or rotating magnetic field at the Larmor frequency through the use of an electromagnetic coil. So think of an electromagnet as we discussed before. We have this loop of wire. Sometimes it's around something that magnifies the effects, but we flow some current through this loop of wire and it generates a magnetic field. If we apply a constant current through it, we'll get a constant magnetic field. If we apply alternating current through it, we'll get an alternating magnetic field. And if you think about it, what is an electromagnetic wave? It's an alternating magnetic field. For a 1.5T magnet, the Larmor frequency will be 63 megahertz, which is, as we said, within the radio frequency range, so we will need a radio frequency pulse. Another conceptual question: why does the radio frequency pulse have to be at the Larmor frequency? So actually all electromagnetic waves will impart a degree of energy to the system. However, things applied at the natural frequency of the system, in our case the Larmor frequency, will most efficiently transfer the energy of the wave to the system. I want you to think about this example. I think this is a little bit more tangible. You've likely heard the concept of an opera singer who can break a wine glass with his or her voice. So this is a picture where we have a wine glass and we have a sound producing machine. And notice that it is perpendicular to the wine glass. We can play sounds in front of this wine glass all day without it breaking, just like you talking in front of a wine glass, right? These don't spontaneously break. But if you can produce a pitch that's at the same frequency that this wine glass naturally wants to resonate at, something interesting happens. The walls of the wine glass start flexing, and they flex more and more until finally the wine glass shatters. This is the same concept that we're using in MRI physics. You can send different frequencies of electromagnetic waves or alternating magnetic fields all day long, and we won't do much to that magnetic field within the body. However, if we apply just at the frequency that this magnet inside the body wants to rotate at, the Larmor frequency, then we'll be able to impart that energy and get it to start precessing. This is a kind of fun one. The Earth has a magnetic field. Can we use it to perform MR imaging? Why not, right? We're in a magnetic field right now. We're standing on the Earth. So the answer to this is actually yes, but you have to remember that the Earth's magnetic field is very weak, and there's a reason the Earth is 0.5 Gauss, that's the measurement of strength of a magnetic field, and a clinical MRI machine generates a magnetic field in the 1.5 to 7 Tesla range, where 1 Tesla equals 10,000 Gauss. So our MRI machines are about 4 orders of magnitude greater than the Earth's magnetic field. So to summarize, we've placed a body in a very strong magnetic field, and if we could look at the protons inside the body, we've noticed that more of the protons have aligned with the field than against. And if we were to add all of these up, they would generate a net magnetic vector in the direction of the applied external field. We then apply an alternating magnetic field in the form of a radio frequency pulse at the Larmor frequency. And when we do this, this net magnetic vector inside the body starts precessing at that same Larmor frequency. So we have figured out our input. Our input to this machine is an RF pulse. So then the next critical question is, what is the output? What does the machine see? So just to orient us to the axes we'll be using for the rest of the lectures, we'll denote the z-axis as the long axis of the body. and the X and Y axes as the cross section of the body. So here's what we're going to do. We're going to place another coil or a loop of wire parallel to the Z-axis. And that's what this animation shows. Let's just say this is all of those protons added up, and here's our X and Y axes, and then the head and feet of the person will be along the Z-axis. And this animation was adapted from the PIRL YouTube channel, so all credit goes to them for the original animation. So what happens when we apply our alternating magnetic field to this net magnetic vector at the Larmor frequency? You can see that we generate a sinusoidal curve if we measure the current over time. And in particular, as this comes closer to the magnet, we get the maximum current. As it goes away, it goes in the opposite direction, and so on. So now we're going to take a look at what happens when we change the angle of the spinning net magnetic vector with respect to the Z-axis. Notice as we change this angle, when it gets closer and closer being completely in the XY plane, we get our maximum deflection. We measure our maximum current. And then when it gets as close as possible to the Z-axis, we measure the smallest amount of current, almost none. And we call this angle the flip angle. Finally, in this video, we're going to see what happens to our measured current as we keep the angle the same, but we increase or decrease the magnetic field. Notice when we increase a magnetic field, we get a higher signal, and we also get a higher frequency. And when we decrease the magnetic field, we get the opposite, a lower signal and a lower frequency. Remember, the Larmor frequency directly depends on the strength of the magnetic field. If we increase our magnetic field, we'll get a higher Larmor frequency as seen in our current graph. And if we decrease it, we'll get a lower Larmor frequency. So, as noted, amplitude and frequency change with increasing and decreasing B0. So this is kind of the aha moment. Like the wireless charger in your phone, MRI machines take advantage of Faraday's law of magnetic induction, which states an alternating magnetic field, in this case our precessing net magnetic vector, induces a voltage and thereby a current in a nearby coil. So this is a very expensive wireless phone charger. So let's think about it. What's going on inside your wireless phone charger? A current's going into the charging pad and then flowing in a circular coil. That creates a magnetic field perpendicular to the coil that increases and decreases as the current increases and decreases. And then that induces a current inside a coil inside your phone that charges your phone. So we figured out what our output is. It's current. But we have to make some modifications to this. Let's go back to this animation. This is our net magnetic vector casually rotating at the Larmor frequency and generating a sinusoidal current with respect to time. Now, do you think this is really how this works? Or let me ask you this. Let's say your car runs out of gas and you're on flat ground and you give it a push. Does that car just keep rolling forever? So the answer is no, right? It'll travel a little distance and then come to a stop. And that's because we have friction between the wheels and the ground. We have these losses that we're never going to get back. We'll lose that energy and the car will stop moving. So likewise, in MRI physics, once we impart this energy to get this net magnetic vector spinning, it doesn't spin forever. In fact, the MRI machine records a decaying sinusoidal current coming solely from the XY plane. And that makes sense, right? We impart this energy, and then those protons are going to interact with their environment, and we're going to lose that energy. We lose this current that we capture in our coil. And this current directly represents something that we call T2 decay of our image body part, and that should sound very familiar. So let's just take another look at this. Again, this is an animation adapted by the PRL YouTube channel. All credit goes to them. And in this graphic, we're looking down the barrel of an MRI machine. And let's just look at what happens to these individual protons after we excite them. Notice that initially all the protons are rotating at the same rate, and then they start interacting with each other. Some speed up, some slow down relative to each other, and with that the signal decays and is lost. Let's just take a look one more time. They're spinning together. They start spinning at different rates, and we lose the signal. And we're not making this up. This is an actual free induction decay curve from a 1.5T machine by Dr. Elster over at MRIQuestions.com. But more specifically, it represents the T2 decay curves of each individual voxel summed together, and this is very important. We have a slice through the body, in this case the face and brain. And this current that we're measuring comes from every single voxel. For example, this voxel here containing mostly fat contributes this decay curve. This voxel here that is mostly soft tissue may contribute a decay curve that looks like this. And finally we go back here to the posterior scalp, and this voxel, again containing mostly fat, will give us another T2 decay curve. But we can't see these individual curves. We can only see all of these added up together. And so that's our goal. Our goal is to deconstruct this raw MRI signal back into their individual decay curves coming from each voxel. Once we find a way to break down this complex signal that our machine records into the signal coming from each individual voxel, we can then choose a time to compare all these individual curves. We'll call the time TE, and we'll use that to calculate the current coming from each voxel at that time point. An example like this. We want to know what these curves are doing at a time of echo of 200 milliseconds. That corresponds to this time point on the graph. So let's say we can measure the amplitude of each individual T2 decay curve at this time point 200 milliseconds TE. We take a measurement, let's say the top one's 9 amps, the middle one's 4 amps, and then the bottom one's 9 amps. We can then use these numbers to build a contrasted image. Because this is ultimately what we're doing, right? We're plugging numbers into a matrix, and the different values of those.
And this is the point where they converting, this decay time, this relaxation time, there is different for different tissues. And that is the number, that is going to be used for the contrast, different numbers, different brightness, or, so on. So this is the key moment here, to understand, how the images are basically created.
Numbers give us our contrasted image. So a few more conceptual questions before we end this first lecture.
Stop using ChatGPT for your research.
Okay. So I'm going to stop here. Let me, is there any question? Anything? One thing I want to point out is when I ask questions, and sometimes, you don't have to get the right answer again. I just want to reinforce that. So the idea is that, remember, science is not about getting the right answer right away. It takes time, for everything, we don't get, sometimes takes years to find what's and understand what's going on with a certain phenomena, So I'm asking difficult questions, and the opportunity for you to reflect and think about is basically the idea of creating a habit of you trying to find answers by yourself. This is basically, the foundation of creativity, and that takes time to learn how to do that, before you look at the what somebody else has already, answered, and then you follow behind that line of thought. But asking a question before looking at what is understood about a certain topic gives you the chance for you to come up with new ideas and probably solve problems, because solution of problems are basically based on new ideas, and not repetition of what is already, no. Is there any question, anything before we close today?
I think I'm all good.
Okay. Yeah, this is a difficult topic. That's one of the reasons that I recorded. The other reason is, I want to post the recording and the PowerPoint presentation so you can revisit. It takes time for you to, absorb all this, but hopefully today you have like a general idea how MRI works, and this is one of the applications of magnetic fields. Just summarizing, a magnetic field is created when you have a current going through a wire. When you have a coil, you can reproduce a magnetic field from like a permanent magnet. You can a moving charge. You need a moving charge, right, to create a magnetic field. And a magnetic field being changing, generates, current in another coil, right? So you can induce a current in another coil, and that is, what we see application with the phone pad or charging, wireless charging, right? So I'm going to stop the recording.